Good morning, everyone. Wait a few moments.
Hi, good morning, sir. Actually, good evening, sir.
Good evening, my friend.
Hi, Lady Sir. Good morning.
Yeah,
Let me
so
know
uh, it's, we can now start again. Already join,
when- Yeah,
or we can wait for another 2 minutes.
yeah, I'll wait.
Okay.
Drinking silence. That's the baby. Okay, so good morning again. Um, this is official talk course. Let me begin by first of all thanking everyone that made the workshop possible. Primarily, Professor Manikaha, Professor Kumar, engines before this. First, thank sponsors that take place. Personally, I would also like else thank you all the I hope second time I hope is that we provided ideas, some inspiration, even sometimes come a shortcut for you problems. Narrative problem and forest uh, matrix. So what I have planned for today is not any too profound. Just would like to remind us all list of there's possible work on. Some of them will be very specific. Take pen and pencil and start thinking right away. Some of them will be far-fetched ideas, but intuition and optimism methods, and hope they prove fruitful in the long run for all of us, especially studies. So, there my so, few ideas, open problem, I'll dare to say wishful thinking about things that can be done regarding the piano classes. I will, I will present the two. They're not in any particular order. Of importance or anything else, no particular order. Because they, um, so one of the things I mentioned for this class is that we did not include hierarchy. Something that hierarchy of mental activity is. Sure, we can make a line, table, but I don't think self understands very well. So um, I want us, I would like personally to understand more class. I think I noted it. What is this? Is the main matrices that are n by n, such that um, for every k goes 1 to down to n, look at the sum of the principal minors of order k. So in other words, the determinant alpha, where alpha 1 subset of 1 up to n, but its cardinality equal to k. But this sum is positive. So remember that these sums are the coefficient of the characteristic polynomial. They're also the elementary symmetric functions. So, for example, the characteristic in one form start with to the n minus the trace. Trace would be this sum where alpha is a singleton. So, considering this class of matrices whose sums of principal minors of any particular order is positive. And of course, if all the principal minors are positive, then sums are. So of course, the P matrices are a subset, a proper subset. So I'm wondering, what is the relation of this? So of course, so matrices, let me read, but matrices hat obey the Kellogg region. That's the region that does not contain the eigenvalue. Right, remember? Okay, Kellogg region A. So the spectrum of A, the K. So in particular, I'm sorry, I should have said here. So you notice that I'm using hat because I believe there must be two hat and two that we have used in the linear, saying they're the same and saying there's some inclusion property. I don't really understand, but I'm wondering what is the relation between Q hat and Q. So Q means that LCP solvable for all little, right? In particular, what is the intersection? Is there is there there um, is there something we can say about the feasibility set of QM or the solution set of QM when M hat? What are these? Something significant about. There is some history because curiosity. They are considered a, how should I say, an important generalization. And there are several open questions about about the, the spectral field matrix we make. So one particular question, for example, is every I'll call it A now, but early parity problem. Every A in that similar to a P matrix. They can be prospectual. We know how P to hat matrix are prospectual. So if you give me, of course, but if you give me a hat matrix, it has the same. It has the same similarity, right? So that is a so that's one area that a little bit into classes and a little parity problem for studying. Since I'm at this, let me mention some other spectral problems that are associated with. Okay, so NQN is spectral questions about P matrices to hat matrices. So there's one particular problem that has been the center of tension, all my still an open problem. So suppose you have a matrix A, square and real, uh, satisfies that K to the K, the P matrix, for all the powers for all K. K equals 1, 2, whatever. For all powers of A are P matrix. Now we have classes. Right? For example, the positive definite. For example, positive definite, the totally positive, all of whose positive principle. When you follow them up, there's also another class, subclass of the M matrix that has. So the question is, all of these classes that we know of have real eigenvalues that are all necessarily positive. Or more generally, all these matrices are positive stable. All matrices know this type are positive stable. Let me remind you what this means. It means that for every eigenvalue of such a matrix, the real part of this eigenvalue is positive. In other words, all the eigenvalues open right hand. So that's the conjecture. That's since the 80s in a paper by Charles Johnson, Daniel Herskowitz, all matrices, all of whose powers are positive. So AK for all K implies that A is positive. So I will mention this as a conjecture and say that I'm always believe that it is, that it's still an open problem that has inspired a lot of work by a lot of people, actually core matrix theorists, but nobody has been able to put together the basic properties, defining properties. All I'm requiring here, very strong statement, is that when you follow them up, they remain people. And the question is, does this are all the eigenvalues right playing? Now, in the work of many people trying to, including myself, we have realized that there is a much weaker assumption might lie positive. And we have not been able, if it's that much better than this one, and if it weren't true, perhaps we would have been able to find a counterexample. So I will present it here not so much as a conjecture, but as a challenge to either prove or find a counterexample. In other words, less confident than stating it as a conjecture. I have less confidence, so the much weaker assumption plus conjecture. Let's suppose that A square are, I'm not going to say all the powers, just the first two. A and A square. Look, you need to calculate. Okay, so does this imply, I'll put a question, does this imply that A is positive stable? Now you would think that this is a very weak assumption to make this A and the square of it. That either there's a proof of this or there's an easy counter. This is still an option. And I'll say here, can you find a counter example? Because I don't believe this one. But nevertheless, there's some mechanism that relate ability of powers affect spectrum of it that we don't know. Therefore, that's why these questions 40 plus years now. So this was conjectured by Johnson Haskell. Now, I've shared some notes that might be circulated and exact formulations of these are also some other related open from the spectrum stated, excuse me, with careful attribution working with. All right. Let me go now something that's perhaps a different nature. Okay? So, as I said, there's no particular order of I'm presenting today. I'm just tapping things that came attention raised the question. So here's another class of problem in opinion, and it would have applications solving linear systems, but also solving complementarity problems iteratively. Okay, so this is an application iterative. I'll leave it vague like that. I mean, for systems or LCP. So perhaps it's no surprise, and it shouldn't be a surprise, but when you have a matrix, form a principal pivot transform, and that's a particular feature of the matrix that results a new matrix with certain nice properties, especially domain and ranges. So it is perhaps expected when you do all the operations that produce the principal, have no expectation about tracking what happens to the, okay? But the reality is somewhat, okay? So when performing the principal pivot transformation of a matrix A with respect to set alpha, it is surprising that there is some tractability in other words, you can tell what happens tractability of how spectrum change. So there's no question mark. We discussed it when we discussed it briefly, but at some day, there's certainly so for example, we can express the characteristic polynomial the PPT terms of A and alpha. Okay? And with an example that you will find one of the papers that I share with you, there's a particular application of it that's very interesting. So, what can happen? Let me tell you what can happen that leads to a general question. We have a matrix A, 10 by n, and it so happens that the spectral radius is not less greater. So this matrix, if you were iteration, find a fixed point, a mapping, for example, if you solve the linearity problem with the NITM method, that method would not converge. So we have divergence of iteration. But it turns out that both in solving a system or solving a linear, there is a way to express the solutions of the system or the complementarity problem in terms of principal pivot transforms, the coefficient. Okay? So this is the following idea that happens. No examples. For examples, you can solve can happen that the spectral radius of the PPT of A with respect to some alpha less than 1 some alpha. Okay? And solutions of linear systems or LCPs are related. Can express the solution of the LCP in terms of the principal pivot transform made. Okay? So the question is, when? And by that I mean, for what alpha subsets of 1 up to n that the spectral radius of the matrix A respect to alpha is. So can we identify, given a matrix, identify when such a principal transform has all its eigenvalues? So you can take a random matrix A, or take it one in one of those, or hierarchical classes show up LC by just make it so that some values have modulus greater than. Find a few of the PP. By the way, on my website, very easy already written file that finds. So experiment, find some alphas and see that occasionally, not always, occasionally, there are some such alphas that will use the spectral radius, something. So the question is, when does this happen? What are the alphas for which? That's, in my opinion, you can view this as a preconditioning. I don't know if it's free, but a condition. So sometimes we solve a linear system, something to coefficient matrix times that becomes advantageous in terms of how you solve that. Scale columns so that it's diagonally dominant. Sometimes you scale it so that becomes better conditioned. Sometimes you scale it and try diagonal. But very advantageous in, for example, finding QR factorizations or trying to find the eigenvalues. So can you think of principal people transformation as some sort of preconditioning of a system so that suddenly an iterative method can become available. As I said, there are some examples, including of how to transform a regular system instead of solving. You solve through fixed point iteration, some system with a very simple idea, very similar to the idea discussed yesterday that gave rise. So that's another class problems. I think is worth examining. Now, just for a change of pace, well, actually, just for a change of pace, I'm going to mention a couple of crazy ideas for which I have no idea if they hold any water or they're worthwhile or if they can be quickly shut down as not so smart, but I'm always compelled to think about it like that. So some very vague suggestions for research. I don't know. I mean, that is the question. Okay, so so recall the notion of a Kronecker product. Know what that is? So you have two matrices, center is Aij, and the sizes don't matter. They don't have to be there. They don't have the same size. So I'm not going to write it down. Then we'll find the Kronecker product. By definition, this is a matrix has as its in corner here A11 times B, and A12 times B, so on. A1N, okay, let's suppose this M by N, A1N times B. So on down here we have a M1 times a M2, so on, a Mn times B. So it's a huge matrix, right? And its dimensions are the products of the dimensions. So you put copies of B everywhere with the entries of A in front. So huge matrix. And it has remarkable properties. Um, remarkable properties. So I don't have time to now list them, but you know, the Kronecker product of the universal Kronecker product, if it's multiple product of forces, you can tell what the determinant is. Very remarkable property. I would say Google or look at the book topics analysis by Horn and Johnson. That's the second book by Horn and has a whole chapter on this, very big chapter, lots of applications and lots. One of the most frequent uses of the Kronecker product is what we expect in. Take a problem, you can make it more linear in its presentation by augmenting its size. So for example, one important product has application matrix equation, matrix and vector equation. And in some sense, the LCP is a matrix and vector equation together with some constraints, right? So for example, let's suppose you have the product of AX equals C. Right? This is the matrix equation X. So X is an unknown matrix, and A, B, and C are given to you. The question is, find the X such that AX and A times X times B equal to make many equations in solution of differential equations form. Well, it turns out that with the operator vec x, the operator vec it takes the columns of the matrix X, puts them one below the other, and creates a right? This is vector with the columns X lined up in one big column. So if you consider this operator, then this matrix equation A becomes a Kronecker product in your system, essentially. Okay? So it turns out that the X, the solution X, satisfies the following linear equation. Transpose Kronecker product A times vec X equals vec C. So we transformed to be kind of like a difficult matrix equation to a very familiar object, a system equation, right? Familiar equation. For example, we know it has a unique solution, the coefficient vertical. All right, so therefore, if transpose K is, and the determinant of terms of the, so that condition for the matrix equation suddenly to have a unique solution, or to have a lot of solutions, or to not have a solution. Vec X is not in the column space of Kronecker product. There's another one, another example where an infamous matrix equation becomes linear. So the equation of the form x times a plus a star x equals h. So let's say a matrix A is given, matrix H is given. It is known that H is positive definite. And if you can find a positive definite solution X, then the matrix A is positive. Okay? What we call a Lyapunov equation. When H is positive definite. We're looking for, if there isn't definite, so it's a condition, if you want to solve this equation, whether it has a positive definite solution X, and H can be anything that's positive definite, it could be identity. It's a necessary and sufficient condition having a positive definite solution. A has all its eigenvalues. Well, it turns out that X satisfies the following equation: A transpose cross Kronecker product plus identity Kronecker product A star times vec X equals vec H. So suddenly the Lyapunov solution, the Lyapunov solution, so the Lyapunov equation, is a linear system. And this matrix here, A transpose cross Kronecker I Kronecker, known as the Kronecker sum of. So there are many others as well, where matrix equations through the Kronecker product become linear equations. Therefore, theory can be developed in terms of very classic results of factory algebra. So here's my idea. It's not developed at all and not even tested. So my crazy idea is the following: is there way to express LCP, the LCP problem, as a matrix equation, and solve it? And by that, I don't mean find a solution as a method to solve it, but develop a theory about its solvability. Really, that if it's to express LCP as matrix equation, and then use Kronecker product. In some sense, I'm taking a linear equation, transforming it complex matrix, and retransforming it Kronecker linear. Played a little bit around with it, wasn't successful. I wasn't ready about the possibility of using Kronecker products. There are other ways, other reasons to consider a Kronecker product. Find a Kronecker product of matrices A and B, where A and B are a hierarchy of positive LCP. What are the Kronecker products? You take, I don't know, a P matrix and find its Kronecker product with a copositive. Take cross the Kronecker product. What if you find a Kronecker product of a P matrix or two Q matrices? Is there something you can? Not necessarily. I mean, this is mostly mathematical curiosity, but usually interesting. I have lots more, but I'll finish with this one, just because so remember semi-monotone matrix. Semi-monotone, strictly. Let's stick to strictly semi-monotone. So for every 0x negative, there exists a k such that x sub k is positive and ax sub k. So it does not, it preserves the positive sign for every non-zero non-negative vector of the same. And of course, P matrices are. We call this class E, right? So suppose we have that P subset of P matrix and there was a conjecture I have not been able to, where I want to explore. A and E, this imply or when, benefit always, when does it imply? That A matrix plus a matrix where B, the P matrix, P is entry-wise non. Clearly, when you take a P matrix, and when you add a non-negative matrix, it changes. Trivial from the general conjecture we had was that all of them are like. I don't know what to. Perhaps it is, perhaps it isn't. Either find a counterexample or study more simply. I think the right thing to do is study semi-monotone matrix. So remember, a P matrix can have lots of negative entries. Could be, for example, an M matrix, where all but n entries are negative. You can add any non-negative matrix, then it remains first. Are there any properties based on this decomposition, and are all strictly symmetric? That's a problem that we mentioned is um, yeah. Another thing very quickly, the role of Haley transfer method. Just for the sake of what we're doing, initiative methods for the LCP. Remember, we saw a special case, presented a special case where the matrix M was positive. Uh, there was an initiative method, worked very well, and it involved the Cayley transfer. So we have M positive definite and involved the K plus M inverse times I minus. I think we all kind of agree that this could apply to every coefficient for which the K. So, particular if M had eigenvalue was positive, that will result into a relation that's convergent. So I think more investigation is needed to general situation. All right, so I'll see any questions you might have.
Yeah, there's already someone who's raised a hand.
Hello, sir.
Hello.
Yeah, so this conjecture for strictly semi-monotone matrices, are does this is there any literature of whether this result holds for like 2x2 matrices or 3x3 matrices? Whether this is true for lower order matrices, whether it is true or not? Any literature about that?
Yeah, I think for small matrices like 2 by 2, so I've shared the paper on semi that basis conjecture has a few preliminary results. The question is when? So it's not so much the conjecture that all of them. The question is, I give restricted when is the sum of it. So that paper is with a and there's some subsequent work that Megan and Professor have done part of that is relevant. Semi-monotonicity type of conjecture. So yeah, so I've sent a few papers that you can post somewhere. And also, if you go to my website, you will quickly find out the work on some of that is there. And I think we have announced the questions.
Yeah, one more.
Hello, sir. In the last, you say something about role of Kelly transformation in iterative method for LCP. So you discussed about PD. So, like, what exactly you want in this case? So, can we generalize this for D matrix also?
Right. So that's my question. So, find particular application that was published sometime in 80, and it applied iterative, applied an iterative method to solve the linear disparity problem. The assumption that was not positive, n was a positive. and entity that will be in the so and it involved daily transfer, and I think the way it involved it transformed developed an iterative method suddenly because being positive definite all the eigenvalues are positive numbers. Transformation makes all the eigenvalues have modulus less than 1. But the method became convergent. And my question was why positive definite? You can apply it to any matrix that has its eigenvalues in the right. That was my question, but it's not so much the particular question, it's more the idea of using daily transformations to work with the matrix hierarchy. I have already an older paper that talks about K. Well, okay. Well, I'll just mention it here. You can find on my talks about Cayley positive M matrices, positive definite matrices. So we characterize all these classes in terms of the Cayley transform. What is an application? Because all these classes show up in the there must this transfer. And I had never thought of it until I saw this very specific example. So I'm saying this is very vague. I prefaced my discussion that I don't have anything. Just saying, investigate. Let your mind fail to how you make daily transformation LC. So some of these things I mentioned are very specific problems in put on a piece of paper right now and start working on them. Some of them require taking a philosophical view, trying to think of potential application of the methods, on the concepts, of the study of the LCP or any other question.
I haven't seen consideration of a dual LCP kind of a thing. Is there something? I have searched on the internet and found one or two articles on what some people call as a dual LCP, but just one or two results. I mean, there is not even a consideration of a strong duality and things like that. So any thoughts on that?
That sounds plausible. My understanding of the concept is more geometry of tones. And as long as you have the right tone in mind, I don't know if it's a physical set or a section of tones, then yeah, duality. Conceptually, right, if a problem is hard, sometimes it's dual problem. So, yeah, but I don't know anything specifically. Well, one thing does come to mind. I was going to mention it as one of the vague ideas. You know, is there a relationship? And, for example, linear anxiety problem used to model negative matrix factorization. And that aspect, if you're talking, for example, about co-positive matrices, we can think also about the dual concept, the completely positive. But I was recently I taught in my class graduate project about negative matrix factorization, and very quickly, first of all, you realize inequality, a problem of inequality, first of all. Secondly, optimization problem that in practice is solved using essentially squares. That's one typical approach. As a meaning for being informed, make a choice in it. So it seems to me like it could be formulated in a negative problem, at least some special cases of it could be formulated as it is quadratic in nature or linearizable. So why not? Never seen any other direction. And this one go in another of my crazy dreams. LC. Sorry. Any other questions? All right. So let you a break. I'll stick around a little bit longer. I need to make a phone call and then I'll join Professor Sivakumar's lecture. Thank you all. And if I don't get to speak to you directly again, best of luck. Hope you have good fruitful careers in charity or writing.
So
Thank you so much, sir.
thank you. Thank you. I think I'm audible. Yeah, so thank you very much for spending your time here and especially managing this time difference. And it's too late, we can see. And very much for first of all accepting the proposal here with us. And this very much interesting, wonderful lecture. And I'm pretty sure that everyone has enjoyed. And particular in my case, I can say that I didn't do much on this matrices, but after your lectures, I can also started become my favorite also. I can see that.
Good.
And PPT also. I mean, I heard the name PPT sometimes in not very awesome. Maybe during my PhD only. Before that, I never heard. But I'm pretty sure here many MSc students are there. I mean, who heard at this level. So I mean something very much helpful for them. And especially today, I guess after your lecture, I believe now everyone has lots of work to do. They got lots of open problem. I'm pretty sure that they will go and start working with the problems, and they email address already been
I hope so.
and Thank you. I mean, I mean, I can see that from 2019 onwards I started this plan, and it ultimately it ended up today. So that was a very nice experience.
You're very kind. Thank you very much.
And we are hoping to see you sometimes here.
Sometime next year, this time, I should probably. Yeah.
So I think this we wanted to here also. Shillong is also a very beautiful place, and I'm not sure whether you visited it before or not. So
I haven't been to the north. I've only been down to the Finland coast.
I thought.
and yeah. Thank you. I don't know if anyone wants to say anything. Okay, I can see that there are participants. They already dropped some message.
No,
They enjoyed. I can see they enjoyed your lectures.
yeah, very good. I'll get some. All right. I have to go grade a start. Final exam was very good. So I'm not very happy with them. All right. Sounds good. I'll see you later.
Yeah. Bye bye.
Bye. Okay, thank you very much, sir.
Another 10,
Sorry, sir.
another 10 minutes?
Another 10
Yeah.
minutes.
Yeah. Okay.
Okay. you are ready, sir, we can start.
Yeah, I'm.
Okay.
So good morning, everyone. So the idea is to continue this discussion on characterizing invertible M matrices, the relevance of M matrices to the linear complementarity problem is was also given in one of the statements that I wrote down yesterday. It is that a Z matrix is an M matrix if and only if it's a Q matrix. Z matrix is an M matrix if and only if it's a Q matrix. So what I do is write this theorem down, the one that I wrote down yesterday, and then prove some implications to highlight the kind of techniques that we use in this theory, and also to consider further the relationship between LCP classes and non-negativity aspects of positivity. I'll be especially interested in invertible matrices, whether they are non-positive, non-negative, what implications do they have for the linear complementarity problem, or at least the classes that are connected to the linear complementarity problem. Okay, so let me write the theorem again. The various statements for a Z matrix to be an M matrix, and remember that an M matrix by definition is invertible. There are many where you can find these statements. One of the most often cited books is the book by Bergman, Non-Negative Matrices in the Mathematical. So what are the statements? Following are equivalent for a following statements are equivalent for a Z matrix. The first is the condition that A is an M matrix. So to recall what it is, then we can a Z matrix is and B for a non-negative matrix, for some non-negative matrix, together with the relationship between the number S and the matrix given by S is greater than the spectral radius. So such a matrix is an M matrix. And what we had seen yesterday was that A is an M matrix, and A is invertible, and that A inverse is non-negative. All the entries of A inverse are non-negative. Statement C is the monotonicity condition. That is, A is monotone. A is non-negative implies X non-negative. Statement D is the requirement that A is a semi-positive matrix or an X matrix. There exists X positive such that AX is positive. Statement E brings in the LCP connection. That is LCP A comma Q has a solution or has a unique solution for every Q. LCP A comma Q has a solution, unique solution for every Q. And the statement F, if I remember, that involves the Cayley transform. Cayley transform is well defined. C of A is well defined. And we call the F, capital F, is a Cayley transform of A, so that is I plus A inverse into I minus. And what follows is that I plus F inverse as well as I minus F. Both these matrices are M matrices. Now, this last statement is not in this book. Even though one of the characterizations involved the transform and the Lyapunov theorem for stability of a continuous dynamical system. This last part is taken from one of Michael's paper, which appeared in Electronic Journal of Linear Algebra. It appeared in 2002. I think positivity classes of matrices. Cayley transform and positivity classes of matrices. That's the title of the paper. So when I was preparing for this, I got slightly different proofs to one of the proofs that he had given in this paper, where he has considered several P matrix classes, M matrices, totally non-negative, inverse M matrices, etc. So if time permits, I will present this last part. And this is not from very much claims. Okay. So this was proved. A implies B was proved yesterday. One just looks at the line of expansion. The matrix B by S is the convergent. That is, fertility of B by S less than 1. So I minus B by S is invertible. And I minus B by S inverse has this binomial expansion. I plus the B by S plus B square by S square, etc. Each term in that expansion is a non-negative. And so this convergent sum is also non-negative. So that proves that A inverse is non-negative. B implies C is easy. If A is non-negative, you pre-multiply this inequality by A inverse, which is non-negative, and so you get X non-negative. C implies D is also easy the moment you observe that B and C are equivalent. B and C are equivalent, that was stated separately yesterday, I think. And so B and C are equivalent, then proving D is easy. All you have to do is to look at A inverse E. E is the all coordinates one vector. If you call A inverse E as the vector E, then V is positive and AD is positive. So that proves C implies D. D implies D involves a little bug, so I'll give that proof. By the way, the proof that I'm going to give is already in the original papers and some other texts. But this will make use of aspects from numerical analysis. I can make use of linear equations, for instance. Especially the Jacobi method that was discussed both by Michael and by me. Okay, so let's see how D implies E goes through. D implies D. So there is positive such that AX positive. So let's define that X be positive such that AX is positive. I'll define a diagonal matrix D, whose diagonal entries are the coordinates of the vector X. This is a diagonal matrix. So this is a positive. A diagonal matrix with positive diagonal entries. It's a non-negative matrix. Look at DE. So what is DE? E is all coordinates one vector. So DE is precisely the vector. D is precisely the vector X. And now I using this matrix D, I call C as the matrix AD. Look at the matrix AD. Let's make the following observations for A as well as C. A is a Z matrix, right? This condition is given to us. A is a Z matrix. So what is a Z matrix? All diagonal entries are non-positive. So just keep the structure, sign pattern, And look at this condition. There exists H positive such that AX positive. This will mean that the diagonal entries of the matrix A all will have to be positive. All the diagonal entries of A must be positive because look at the first row, first entry. If that is less not equal to 0, then you can't find an X positive for which A is positive because along the first row, except the first entry, we know that all other entries are non-positive. And so if you multiply that with take the dot product of the row vector with the vector, and if the first entry is not equal to 0, this condition will never be satisfied. So all the entries of A are positive. So let me make that observation here. AII is positive for all I. And look at the matrix C. The matrix C is a product of A with D. If you look at the diagonal entries of C, what can you say about the diagonal entries of C? So the first diagonal entry, for example, is the dot product of the matrix, the first row of the matrix A, with the first column of D. The first column of D, which is just the column 1, 0, 0, etc. So it is the dot product of the first row of A with the column vector x1, 0, 0, 0, etc. So it is just the dot product of the first diagonal entry of A with the number x1. And that is positive. And so, not only the diagonal entries of C are also positive. So let me write this also. CII is positive for all I. We will need this. Further, if you look at the dot product of the first row of A with the second column of A, for example, I want to show that I want to give an argument to the fact that C is a Z matrix. A is a Z matrix. You multiply A by a positive diagonal matrix, then the resultant is also a Z matrix. So let's just look at the first row, second entry. How do we get that? First row, second entry of the matrix C. So it is the dot product of the first row of A with the second column of A. And if you look at the second column, the first entry of the second column is 0. The second entry of the second column is x2. All other entries are 0. This x2 multiplies with the A12. A12 is less than or equal to 0. X2 is positive. So this entry is less than or equal to 0. So C is the Z matrix. So I've just given the argument for the C12. This extends to all the off diagonal entries. So C is a Z matrix. I hope that's clear. So A is a Z matrix, and since A is semi-positive, the diagonals of A are positive. C defined in this manner is also a Z matrix and also has the property that its diagonal entries are all positive. Now, if you look at CE, so what is CE? CE is E is the all coordinates one vector. So what we're looking at is the row sums of the matrix C. C is the vector, column vector. So the column vector, each coordinate corresponds to the row sum, the corresponding row sum of the matrix C. So that is CE. Now CE is by definition, it is ADE. And DE is X. So this is AX. And this is positive because AX is positive. So the matrix, the row sum of the matrix C. Each row sum is positive, and so that's what comes out of this. This means that C is strictly diagonally common. So this is where we bring in Jacobi iteration. So this means that C is diagonally common. So how does it follow? C is positive. Let me write this inequality in this manner. 0 less than. I'll just look at one coordinate. I'm looking at coordinate of C. That is summation j equals 1 to n. Cij. This is the ith coordinate of CE. Okay. And I split this as CII plus summation j not equal to I Cij. I am separating out the diagonal term. And then push this to the right hand side. So what I get is the CII strictly greater than pushes to the left hand side minus summation j equal to 1 to n, j not equal to pi, Cij. But observe that C is a Z matrix, and so the off diagonal, this term includes only the off diagonal. of the ith row. And so the off-diagonalities are non-positive. That means if you look at the modulus, summation j not equal to I, absolute Cij is minus Cij. So I can replace this by absolute Cij. Now remember, each Ci is positive, otherwise this does not make sense. Each Ci is positive, so that's consistent with. We need to know that Ci is not positive. So C is strictly diagonally dominated. This is what this is true for all I. So C, which is the matrix AD, is strictly diagonally dominant. It is strictly diagonally dominant. So I'm appeal to Jacobi for the matrix. We discussed Jacobi for the matrix A. I will appeal for the matrix B, and then conclude that B implies C. I am not proving B implies C. I want to prove B implies C. I'll prove E implies B. I'll prove E implies B next, but I want to prove B implies C, okay, not E. So this is a strict dominant matrix, and so one can talk about Jacobi iterative C. Maybe I write that here. So if you look at a split for the matrix C, we will consider a splitting for the matrix C. Start with the Jacobi iteration for A. Then AD is the matrix C, that is MD minus ND. And as the Jacobi iteration tells us that M inverse exists. So how do you choose M? M is a matrix. M is a diagonal matrix whose diagonals are the diagonal entries of A. So this is the Jacobi method, Jacobi technique for A. You can apply this if you know that the diagonal entries of A are positive. We are in that situation. But to look at what's happening, I'm looking at the Jacobi technique applied to the matrix C, which is AD. And AD is just MD minus ND. I can write this as MD into I minus MD inverse ND. And further write A as MD into I minus K into D inverse. So I have written everything in terms of A now. I have written everything in terms of A. D is positive, so D inverse is positive. D is positive, M is positive. M is just the diagonal of the matrix A. What about I minus K? What is K here? K is this matrix. K is MD inverse ND. So that is D inverse M inverse N into D. D inverse M inverse N into D. Now what is N? Look at what M is. M is the diagonal part of A. So N, which goes to the minus sign, the off-diagonal part of A. So is it clear that N is non-negative? In this situation, N is non-negative. N is so N goes to the minus sign here, and that is nothing but the off-diagonal part of A. The off-diagonal part of A is what? Diagonal entries are 0. Off-diagonal entries are what? A11, sorry, A12, A13, etc. Those are all non-negative. So that you take the minus sign outside, you will get the matrix here. And so N is a non-negative. So what follows is that this K is non-negative. A is a non-negative matrix. Because M is non-negative, M, D are diagonal matrices. So they are positive, non-negative, and the inverse are also non-negative. The only thing that I wanted was what is the N? N is non-negative, so this product is non-negative. So K is non-negative. And the diagonal dominance tells us that C being strictly diagonally dominant tells us that spectral radius of K is less than 1. So this is just Jacobi method. This is a Jacobi method for the matrix C, which I am making use in considering this considering the original matrix K that we started with. So since C is strictly diagonally dominant, by Jacobi method, spectral radius of K is less than 1. And so if you look at go back to this equation then, what this tells us is that this is invertible, this is invertible, this is invertible. Spectral radius K less than 1, so I minus K is invertible. So A is invertible is one thing. And if you look at A inverse, it is a reverse order law that applies. It is D into I minus K inverse into D inverse into M inverse. I minus K inverse goes with the binomial expansion, and it is I plus K square, etc. That is non-negative because A is non-negative. Everything else is non-negative. So A inverse is non-negative. I hope the proof is clear. So what we are doing is to apply Jacobi method for the matrix, which is obtained from the vector X, which is the semi-positivity vector for the matrix A. So this is the I would like to say a new analysis connection to the consideration. So A inverse is non-negative, and we know that if A inverse is non-negative, then A is monotone. So those conditions are equivalent. Remember that semi-positive matrix need not be even invertible. You can just look at the all entries 1. Semi-positive matrix need not be invertible, but if the matrix is also originally a matrix, then such a semi-positive matrix must be in fact an M matrix. Its inverse is non-negative. That is the implication from this concept. I think I include one more proof here, which involves linear complementarity. So let me use this force. So that is statement E. Right? So statement E is that E implies, so what do I want to show? E implies that A inverse exists and A inverse is non-negative. What is statement E? LCP A comma Q has a solution, has a unique solution. Just a solution is enough for me. LCP A comma Q has a solution for every Q. I want you to recall what is LCP. If LCP A comma Q, right? It is asking if there exists a vector non-negative, such that AX plus Q is non-negative, and that the dot product of X with AX plus Q must be 0, the complementarity. Now, whether it is plus Q or minus Q doesn't matter. The moment you know that LCP A comma Q has a solution for every Q. So I miswrite that. If plus Q or minus Q doesn't matter because LCP A comma Q has a solution for all Q. And I will also make use of the Z property generalization that I had given yesterday. That is, A is a Z matrix if and only if whenever X non-negative, Y non-negative, and X and Y are complementary, then the inner product of A with Y is a non-positive number. X non-negative, Y non-negative, X transpose Y equals 0 implies X transpose AY equal X transpose A transpose Y equal to less than or equal to 0. So that's something I'm going to use here. Okay. So let's look at the case when Q is minus E. E is the all ones vector. Take Q to be minus E. LCP A comma Q has a solution. This means that there exists X non-negative such that I'll call this as W. that is W equal to AX minus Q non-negative together with the complementarity condition. Yeah. Together with this complementarity condition, note that I have used Q equal to minus, I'm sorry, I want to take Q equal to E. I want to take Q equal to E and then use a minus sign. This means I'm going to use X non-negative, W non-negative, X transpose W 0. So I have 0 less than or equal to AX comma W. This is the Z property. This is the Z property that I'm making use of. And this is AX is a W plus Q. So it is the inner product of that with W, which is nothing but non-W square, the Euclidean, plus the inner product of Q with W. This is what it. This is using the equivalent characterization for a matrix. Now, look at what you have on the right hand side. Non-W square, this is a non-negative number. And then look at the second inner product of Q with W. Q is the E, all coordinates 1. W is a non-negative vector, so that the product must be greater than or equal to 0. So this is also greater than or equal to 0. So on the right, I have non-negative number, on the left, but it's supposed to be less than or equal to 0. The only way this can happen is that each term is 0, in particular W equal to 0. So W equal to 0, and go back and look at what W is Q. W is AX minus Q. That is, what is it that we have to? There exists X non-negative such that AX equals Z. There exists X non-negative such that AX equals Z. At this moment, X being non-negative is not so important. What is important is that E is in the range of A. The all coordinates 1 vector is in the range space of A. It's the linear combination of the columns of A. So what is the meaning of this? If you look at E, the all coordinates 1 vector, it is an interior point. It's an interior point of Rn plus. What is the column space? The range space is the subspace of Rn. We are looking at square matrices. Range of A is the subspace, and I have this subspace has the property that there is an interior point. Now this can happen if and only if the subspace is the whole space. Okay. Otherwise, the subspace cannot have an interior point of the whole space. It will have relative here, that's a different matter, but it cannot have an interior point of the space unless it is the whole space. This is something that's true even in infinite dimensional space, infinite dimensional nonlinear space. It cannot have an interior point unless it's the whole space. This means that range of A is the whole of Rn. Range of A is the whole of Rn. That means what A is invertible. Parameter dimensions here. It is onto. As the linear transformation is onto, it is squared, so it's also injective. So A is invertible. So this part is there. A inverse exists comes through. A inverse exists comes through. Now we look at the meaning. So A inverse is non-negative. What is the meaning of saying A inverse is non-negative? This is the same as stating that whenever U is non-negative, A inverse U is non-negative. That is the statement. A inverse leaves the cone Rn plus. A non-negative matrix by definition has all entries, all its entries non-negative. An equivalent formulation is that if B is a non-negative matrix, then B of Rn plus is contained in Rn plus. Rn plus remains under B. So this is what we need to show if this were to be shown. But if you go back and see what we have done, we have taken Q to be this vector. The proof can be imitated for any Q non-negative. Take any Q non-negative. Take any Q non-negative. What this tells us is that there exists an X non-negative such that AX equal to that Q. Now X is non-negative and A is invertible. So what this tells us is that X equal to A inverse Q is non-negative. That is, for every Q non-negative, we have shown that A inverse Q is non-negative. And so A inverse is non-negative. Also, I'm not writing this argument. We have proved it here. So I hope this part is clear. You start with a non-negative vector q, then from what is the only thing that we have used here, that q is non-negative. So that the dot product of q with this vector w is non-negative. So this proof carries over if you take q to be non-negative. This last part tells us that the equation equal to q for q non-negative has a non-negative solution. Since A is invertible, this tells us that x equal to A inverse q, that is non-negative. So q non-negative inverse q non-negative. So A inverse is a non-negative matrix. Okay, so this reformulation of this Z matrix thing is crucial here. What about this last part? The last part is telling us about the Cayley transform. So let me give a quick proof of that also. The proof that's given in involves this argument about the fact that a matrix M is an invertible, is an M matrix, then it is positive stable. The real part of all the eigenvalues of an M matrix, the real parts are all positive. So, but here is the proof that doesn't involve, it's just inequalities are used. So I'm now looking at just the last part. So what is the last part? What is that statement? Cayley transform is well defined. I plus A inverse into I minus A. That is the matrix capital F. This is well defined. Cayley transform is well defined, and that also I plus F inverse and I minus F are M matrices. Are M matrices. So Cayley transform is well defined, is done. I will not do that. I just want to prove that these are M matrices. The proof that these are M matrices can be proved by using inequalities. You don't need the real part of the eigenvalues of A to be positive. So here's the proof. So what is the implication that I want to do? A implies F. What is statement A? A is an invertible M matrix. A is an M matrix. Now, I want to prove the other. Sorry. I want to show that, yeah, this is the part that is different from what is given there. So I want to show F implies A. A is an M matrix. The relationship between A and F. So what is given is that the Cayley transform is well defined, and that I plus F inverse and I minus F are M matrices. I want to show that A is. This is the indication. So this is a statement that I want to prove. Cayley transform well defined. These two are M matrices. I want to show that A is an M matrix. Okay. Now that is this formula that connects A and F. That is U 2 times I plus F inverse minus I, if I remember right. 2 times I plus F inverse minus I. That's a matrix A. This is a relationship between the Cayley transform and the matrix. I want to show that this A. I want to show that this A is monotone. Then why? Because A is already a Z matrix. A is the Z matrix that follows from here. I plus F inverse is an M matrix. So for the first term, the offering are non-positive. You are just taking the minus. I is non-negative. So A is a Z matrix from this structure. A is a Z matrix. I simply show that A is monotone. So claim that AX non-negative implies X non-negative. This is the claim that I'm making. So let's start with AX non-negative. A is 2 times I plus F inverse minus I into X. So this is the matrix 2 times I plus F inverse X minus X. So let's call Y as I plus F inverse X. Then X equals Y plus Fy. And so if you go back to this calculation, this is 2 times Y, I plus F inverse X, minus X. That is minus Y minus Fy. And so this is Y minus Fy. And that is just I minus F operating on Y. So I'm starting with AX non-negative. So substitute A into this. I plus F inverse X is denoted by Y. Then this is the calculation in terms of Y. So this is Y minus Fy, that's I minus F operating on Y. I minus F operating on Y is non-negative. I minus F is an M matrix. That's given to me. An M matrix is monotone. So this implies that Y is non-negative. This implies that Y is non-negative. Go back to the definition of Y. 0 less than or equal to I plus F inverse X. That's the vector Y. Again, use the fact that I plus F inverse is an M matrix. So I plus F inverse is monotone. And so from this it follows that this part must be non-negative. And so we started with AX non-negative. We have shown that X is non-negative. So this A is a monotone matrix. It's also a Z matrix by definition. And so I can use this equivalence to conclude and A is an M matrix. So this is different from what was given in that paper. So this more or less concludes this discussion on calculation of M matrices. There is also a set of statements that are true for M, which I'll write down. There are several characterizations, as I mentioned. I've just picked a few to explain this relationship between LCP and positivity, like non-negativity of the inverses. I also have the following, so let me just write this down. Properties of M matrix. Properties of M matrix. Suppose A is an M matrix. Then one has the following. A is positive stable. A is positive stable. So what is the meaning of this? The meaning is that if lambda belongs to spectrum of A is the set of all eigenvalues of, then the real part of lambda is positive. Real part of lambda is positive. So that's the definition of a positive stable matrix. So A is an M matrix, then A is a positive stable matrix. Positive stable matrices are important from many contexts. One context was mentioned by I also mentioned it yesterday. It's about stability of asymptotic stability of continuous dynamicals. That is characterized by positive stability or negative, whether you're looking at A or minus A. Second property for an M matrix is that every principal submatrix of A is an M matrix. Every principal submatrix of A is an M matrix. Just like the property that we have for P. property C is that all principal minus. Why just proper? All principal minus of A are positive. So A is a P matrix. So A is an M matrix, then A is a P matrix. But you can have P matrices which are not M matrices. You can have P matrices which are not M matrices. That is P matrices which are originally not Z matrices. That's possible. But these two classes coincide if you are in the class of Z matrix. All principal minus of A are positive. There is a converse statement for this. That's the converse statement. If A is a Z matrix, and if all the principal submatrices, all the principal minors of A are positive, then A is an M matrix. So statement C and B apply when A is M. Statement C, the first part applies when A is M. The second part tells you that a certain converse is true. That is, if you take a Z matrix with the property that all the principal minors are positive, then the Z matrix that you started with must be an M matrix. Okay. Again, this is a statement that I don't want to get into the proof of statement. But let me give one. One method of constructing M. Looking at the very first representation. That is, you have A equal to Si minus B, where B is a non-matrix. Yeah.
Sorry, last one. Intersection.
Yeah. That's correct. Intersection P, that is M. In general,
The intersection P is contained or
yeah, the intersection precisely M. The intersection P is precisely M. Z intersection Q is precisely M. Z intersection S is precisely M, etc. That's what we have proved. Okay.
yes, sir.
Z intersection monotone, that's an M. All these equalities follow from this consideration. See, M matrix. So if you look at equation A equal to Si minus B, B is the non-negative matrix. S is a number that's strictly greater than the spectral radius of B. Then that tells us a way of constructing M matrices. What is that method? Look at the non-negative matrix B, especially a stochastic matrix. That is, all the entries are non-negative, and that the either the sum or the column sum is 1. Take a non-negative matrix, and then include this extra condition that either the row sum or the column sum is 1. And I'll take it in such a way that it's an irreducible matrix, non-negative irreducible matrix. Let's say B is 1 by 2, 1 by 4, 1 by 4, etc. Take the symmetric case for simplicity. I done with 1/4 here. So the row sum is 1. B is non-negative, and that the row sum is 1. It's irreducible. Since the row sum is 1, 1 is an eigenvector. The origin 1 vector is an eigenvector. B is E. B is irreducible, non-negative. 1 is an eigenvalue with the property that there is a positive vector associated with 1. Then it follows that 1 is a spectral radius of B by Perron-Frobenius theorem. By Perron-Frobenius theorem, it follows that 1 is a spectral radius of B. So if you look at the matrix A, that is something like Si minus B, where S is strictly greater than 1, then this matrix A, by the first condition that I wrote down, is an M matrix. Okay, so this is one way of constructing M matrix. Exploiting this structure, sign pattern, A equal to Si minus B, together with the relationship between S and B. Okay, so this is one way of constructing M matrix. Let's look at, so this is, I think with this I stop with the class of M matrices. Remember that M matrices are Z matrices for which A inverse is non-negative. M matrices are Z matrices for which A inverse is non-negative. There is no other Z which, see, if you take a non-singular Z, the moment the inverse is non-negative, it will have to be an M matrix. Now there are non-singular Z matrices which have the property that the inverses are non-positive. There are non-singular Z matrices. So non-singular Z matrices, there are two types that you can consider. One is the inverse is non-negative. The other one is the inverse is non-positive. Inverse non-positive correspond to what are called as the Fiedler class matrices. I'll not get into that. The spectral radius condition S is greater than D will not be satisfied. You have a condition involving the spectral radius of the n-1 cross n-1 principal submatrices. So the number S is greater than the spectral radius of the n-1 cross n-1 principal submatrices, and it is less than the spectral radius of B. Then matrices of that type, Si minus B, come under what are called as Fiedler class matrices. The one that I mentioned just now will have the property that if it is non-singular, then its inverse is non-positive. Okay, so there is a whole study of such matrices. So one can go for the n-1 cross n-1 principal submatrices. One can go for n-2 cross n-2 principal submatrices, etc. Up to the principal submatrix of order 1. So you have a whole class of Fiedler matrices to the left of the spectral radius of B, depending on the together with the conditions on the principal submatrices of order n-1, n-2, etc. But without getting into C matrices, I would like to also look at 2 or 3 matrix classes which have some kind of a sign pattern property. So one is the class of all non-singular matrices which have the property that the inverse is non-positive. Because I'm not imposing any Z condition now. For the Z condition, when I impose non-singularity, I am interested only in the consideration when the inverse is non-negative. Now, without the Z condition, there are matrices. Of course, you have invertibility. Without Z condition, you have invertibility. Inverse is non-positive. Is there a connection to linear complementarity class matrix? There is a connection. There are also 2 more classes that are related to LCP, the class of N matrices, and the class of what is called as S0 matrices, about which I briefly explained yesterday. Okay, so what I'm trying to do in the next part is consider these three classes. So I'm restricting my attention to invertible matrices. Invertible, which are in Z, I'm looking only at the case when the inverse is non-negative. That is the M matrix class. General invertible, non-positive or non-negative, I look at the non-Z class. So it does not have to be in Z. If it is in Z, then it corresponds to what are called as the Fiedler class matrix. So can I stop here and can we resume after about 10 minutes? Sorry.
Yeah. Then
Can you just repeat what you said?
yeah, I said that can start after 10 minutes.
Yeah. 10:20.
Okay, yeah.
So, yeah, can I resume? Yeah, okay, thank you. Okay, so three matters that I want to discuss next. The first one is generalization of semi-positive matrices, where you allow AX to be non-negative. Some coordinates of AX be 0. So there exists X non-negative such that AX positive, semi-positive. So we call that A is semi-positive. SP if there exists X positive such that AX positive. There's a slightly more general class that has also been considered. In fact, in the original paper of Fiedler, the 1962 paper, generalizations of monotonicity. So he calls that as class S, whereas matrices that satisfy this condition are called S. But in order to be consistent with this notation, semi-positive, I call those matrices semi-non-negative. There is a new definition here. Matrix A is said to be semi-non-negative. That's my own nomenclature here. If you don't like it, just leave it. A is said to be semi-non-negative because we are talking about X. I can call it S. Semi-non-negative if there exists X non-negative such that AX is non-negative. So your requirement on the vector A to be positive for semi-positive is relaxed, be non-negative for a semi-non-negative matrix. One example of a semi-non, of course, there are several examples. The following: if we have A as 1 minus 1 minus 1 1, then this is in some sense an extreme example because for this matrix, AE is 0. The central matrix, sum is 0. The row sums are 0. So E belongs to the null space of A. So this is an example of a semi-non-negative. There exists X non-negative such that 0. There exists X positive such that AX is 0. So this is an example of a semi-non-negative. We can do a few more. What about 1 0 1 0? This is also semi-non-negative. All the entries are non-negative. So just look. Then AE is the matrix 2 0. So this is another example of a semi-non-negative matrix. Just like how one can talk about minimal semi-positive matrix, one can talk about minimal semi-non-negative. Again, this idea was employed by Fiedler and that paper. The only thing is that they did not use this nomenclature. I'm using this nomenclature to be consistent with the minimal semi-positivity that was discussed by Michael. So the terminology that is by Fiedler and Park is irreducibly S naught. So instead of that, irreducibly has some other connotation. So I'll not use that terminology. I'll use minimal semi-non-negative. Let A belong to S10. A is a semi-non-negative matrix. Then A is called minimally or minimal semi-non-negative. Minimally semi-non-negative. No column deleted submatrix of A remains in Sn. If no column deleted submatrix of A, you remove a column, then it loses the property of being semi-non-negative. No column deleted submatrix of A remains in Sn. So I can call it M, just like MSP for minimal semi-positive. Now, if you look at example 1, you can delete, you cannot delete the second column to make it non-negative matrix, because let's say you remove the first column, then you have a negative. Just look at the second column alone. You have a negative entry. You multiply that by a vector, in this case a number. You will still get, you will never get a non-negative vector. So the first one is not minimally semi-non-negative. Is that okay? What about the second one? Second one you can remove either of the columns. You can remove either of the columns. It will remain. It will remain. So it is not. A is in Sn, and there is a column deleted submatrix. Either this or this. It is still semi-non-negative. So it does not belong to this class. It does not belong to this class. There is a result that exactly parallels the result for a semi-positive matrix. There is a result that parallels the result for semi-positive matrices. That is, if you take a square matrix, then it is minimally semi-positive if and only if it is invertible, and inverse is non-negative. There is a result for Sn also. A in MNR is minimally semi-non-negative if and only if A inverse exists and A inverse is non-negative. Minimally semi-non-negative if and only if A inverse exists, A inverse is non-negative. So this is one of the results of A belongs to MNR intersection Sn. I must have Sn in the first place. A belongs to Sn. Let me just write it as A belongs to Sn. A belongs to Sn is minimally semi-non-negative. If not be the inverse exists, the inverse is non-negative. This was one of the results that was proved by Fiedler. He also considered Fiedler and Dark in that paper. He also considered the singular case. What happens when the matrix is singular, and what happens when the matrix is singular and this semi-non-negative? But this general question of asking what happens to the sign pattern of either the Morgan-Ross inverse or the group inverse when A is the Sn matrix singular, that part has not been addressed. So that's one little question that one can investigate. So the reference for this result and this motion is Fiedler and Park's paper, the 1962 Checkmate journal paper. There, after the result for the invertible case, the result for the singular case, but it doesn't have any consequences for either the Morgan inverse or the group inverse. So that's one open question that one may be interested in looking at. So this is one class of matrices. Again, this non-negative inverse being non-negative is the consideration. And there is no Z structure here. It is general inverse non-negative. So this is one class of matrices. Matrices that were referred to by Fiedler and Takas, S0 matrices. just want to point out that this result along with some of the results for M matrices were proved by T.S. Raghavan. This paper appeared in Linear Algebra Application, where he used game theory technique. So this is the game theory proof for some of the results for M matrices, where he has also proved this result using game theory technique. Okay, there is another class of matrices. This time, the matrix is invertible and inverse is non-positive. The matrix is invertible, inverse is non-positive, no Z structure. So that's the second class, which is A inverse exists and A inverse is non-positive. So there is a classification of this matrix class involving linear complementarity problems, and this is a nice speaking result. This we proved in one of our papers, one of my papers with Sushmita. This appeared in the Annals of Operation Research. I think the title is TP's contribution to the linear complementarity problem. So there's one section where we discuss several positivity results, examples, counterexamples, in which we prove the following connection with the linear complementarity problem, especially the matrix class Q0. Well, let me state that result here. The following statements are invalid. Statement A is that A inverse exists and A inverse is non-positive. A inverse is non-positive. All the entries of A inverse are less than or equal to 0. Statement B is that you have this monotonicity condition slightly reversed. Ax non-negative implies x less than or equal to 0. Statement C, for every q non-negative, there exists x less than or equal to 0, such that Ax equals q. The system Ax equal to q has a non-negative solution for every non-positive right-hand side vector, which is the same as saying the system Ax equal to q has a non-positive solution for every non-negative. Statement D brings the LCP connection. For all q in Rn for which LCP A comma q has a solution. For all q for which LCP A comma q has a solution, that is, whenever LCP A comma q is feasible for some vector, then what is the conclusion? Then there exists x in Rn such that there exists x non-negative such that Ax plus q equals 0. There exists x non-negative such that Ax plus q equal to 0. So just it is sometimes called omega kind of a result. What is LCP? Given a q, does there exist a non-negative such that W is non-negative, W is Ax plus q, and one also has the complementary the product W, x is 0. What this tells you is that whenever it is feasible, it is not only that there exists a solution, the solution W is 0. Solution W is actually 0. That's what this last statement implies. Okay, this is a kind of an extreme situation. It is not as though every time you get, but if the matrix has the property that it is invertible and the inverse non-positive, then this is true. Of course. If you look at it closely, what this means is that an inverse non-positive matrix is the Q0 matrix. An inverse non-positive matrix is the Q0 matrix. Are you with me? So what is the Q naught matrix? Whenever it is feasible, it has a solution. What this last statement tells you is that whenever it is feasible, it has a solution already. The solution W is also zero. Okay, there is an extra property for the solution W. There is X non-negative such that W equal to Ax plus Q equals 0 also. So an inverse non-positive matrix is always a Q naught matrix. As a consequence, A inverse does not equal to 0. Assuming A is invertible and that the inverse is non-positive, this implies that A is a Q naught matrix. There is a question which can be attempted here, which is that if A is a Q naught matrix, which is not a Q matrix, remember that Q matrix is a Q naught matrix. Q naught is a larger class. Q naught is a larger class. Q matrix is what LCP A, Q has a solution for all Q. Q naught is, whenever it is feasible, it is solvable. Q naught is Q naught has Q as a subset. So I want to look at a matrix which is in Q naught but not Q. The larger set, it doesn't belong to Q. I want to look at a matrix which belongs to Q naught difference Q and ask the following question. Is it necessary that such a matrix is invertible? A matrix that belongs to Q naught but not in Q, is it necessary that such a matrix is invertible? If it is invertible, can we conclude that the inverse is non-positive? So that will be the converse of the statement. Is it necessary that A belongs to Q naught difference Q implies A is invertible? If so, can we prove that such a matrix is non-positive so that the converse is true? If it is not invertible, if you can find examples of matrices A in Q naught difference Q which are not invertible, then can we say something about either the mode inverse inverse or the group inverse? Whether they are non-negative or they satisfy more general conditions of non-negative. So that seems to be at least morbidly question. You can try that. There are some researchers here. Try this question out. That is another class. I go to third class in a short while, but let's look at a proof of this result. Let's look at the proof of something like, let's say, A implies D. A implies D. First, A, B, C, that's a routine kind of thing, similar to what we had discussed. Yeah. Okay, so quick proof of that fact also. So A implies D. So give me a minute. Some noise out. A inverse is less than or equal to 0. So let Q be such that LCP A, Q as a solution. That means there exists, let's say, U non-negative, such that vector V, which is defined as AX plus Q, that is also non-negative, and then the product of V. This is V. Now look at this equation, B equals AX plus Q. This means A inverse B is X plus A inverse Q. This tells us that A inverse, I'm sorry, I'm using a different notation here, AU. So this is B plus A inverse Q. I'm sorry, this is U. A inverse B equals U plus A inverse Q. So if you look at A inverse Q, that is A inverse B minus U. Now A inverse is non-positive, B is non-negative, and so A inverse B is less than or equal to 0. A inverse is less than or equal to 0, B is non-negative, so the product A inverse B is less than or equal to 0. U is non-negative, minus U, that is non-positive, so this whole thing is less than or equal to 0. So this A inverse Q is less than or equal to 0. The vector A inverse Q is less than or equal to 0. I'll define X as minus A inverse Q. Then this is non-negative, and AX plus Q equals A into minus A inverse Q plus Q. That is 0. This is what we wanted to show. For all Q for which A comma Q has a solution, there exists X non-negative such that AX plus Q equals 0. This is what we were required to show. So the other B implies A needs to be, but I am leaving that for you as an exercise. So this is another class, a class of matrices for which A is invertible and A inverse is non-positive. This is very much connected to LCP. In fact, a subclass of Q0 matrices, namely that the vector W becomes 0. For the solution X, the vector W becomes 0. There is some name for such matrices, non-degenerate matrices and things like that, but I'll not get into it. But the converse question remains. Converse question appears to be an interesting one. Okay, finally, I have the following. At this point, maybe I'll mention one more little result, which you can I'll state a result and state an open question there also. This is the following. This result was proved by Values Phi. He has solved many problems in connection with the linear complementarity problem. Values Phi, he proved the following. If so, it's a necessary condition for a matrix to be a Q matrix. So he proved that A is a Q matrix. Then, if you look at the matrix B, which is identity minus A. So this is a is a square matrix. Identity minus A. This is a rectangle. He proves that this has a non-positive right inverse. He proves that such a matrix has a non-positive. If A is a Q matrix, then this matrix has a non-positive. You can look at the paper that we had written, which appeared in 2020. There we have given the reference for this result, and we also proved this result there. This was originally proved by in his one of his papers, which appeared in linear algebra application. So this is a necessary condition for a matrix to be a Q matrix. We would like to ask the following question: is there something like a converse? Okay, such a converse will be very interesting. So you are giving a sufficient condition for a matrix to be a Q matrix. So any converse will be quite interesting. What kind of a converse can be given for this implication? That's one question. The other question is, what is the Q was contained in Q0? What kind of analog for Q naught matrix. A belongs to Q naught. Then is there an analog of such a result for Q naught matrices? Is there an analog of this? The analog of this second statement. The rectangular matrix identity minus A has a non-positive right in this. Okay. Similarly, for that analog, where the converse is true, things like that. Finally, I have the following. This will probably be the last matrix class that will be introduced in this course. Matrices are called, what is N? Similar to P. So what is a P matrix? A matrix is called a P matrix if all its principal minors are positive. A matrix is called an N, real matrix for our consideration. It's called an N matrix if all the principal minors are negative. Okay. Now these two notions are not negative of the other. These two notions of N and P are not negative. Okay, that's an immediate that follows immediately. So what is an N matrix then? All principal minors are non-positive. So the question is, what kind of results that are true for P matrices that hold for N matrices? So N matrices also have a strong LCP connection. There are several LCP connections for N matrices, depending on whether they belong to a certain type or not. Okay. To begin with, an N matrix is invertible, right? Because all principal minors are negative. In particular, the determinant is not zero. This is invertible. Now, what can be shown is that the inverse of an N matrix, what is called as an almost P matrix. I'll not get into that. Let's focus on N matrix. For N matrices, there are two types. Type 1, type 2. Type 1 is this N matrix has the property that for the matrix as well as the inverse, there is at least one positive entry. For the matrix as well as its inverse, there is at least one positive entry. That is called a type 1 matrix. If you want an example, I can give you one. What is a type 1 example of a type 1 matrix? All principal minors are negative. All principal minors are negative. The matrix, both the matrix A and the inverse have at least one positive entry. So if it is at least one positive entry, it can be shown that it has to be at least two. The number of positive entries be even always. So let me give an example here. So first you can find this is an N matrix. That is all the principal minors are negative. This is a type 1 N matrix, which means that A and A inverse have at least one positive entry. There is a notion of okay, this is not an N matrix. This belongs to the category. Next, there is a notion of what is called as an almost N matrix. There is a notion of what is called as an almost N matrix. So what is an almost N matrix? All the principal minors of the matrix A up to order N minus 1 are negative, whereas the determinant is positive. That's an almost N matrix. An almost N matrix analogous to an almost P matrix. All principal minors are negative. An almost N matrix has the property that all principal minors are negative. Determinant of the matrix is positive. Such a matrix is called an almost N matrix. This is an almost N matrix of order 3. For an almost, we have the following result. These are difficult results to prove, and this theorem is due to T. Parthasarathi and Ravindra. These follow as this theorem follows as a consequence of several lemmas that look like Farkas alternative, etc. So what is this theorem? One again for almost n matrices, one can talk type one. Type one is an almost n matrix with the property that again remember almost n matrices are invertible. So type one is A is an almost n matrix of type one if A and A inverse both have at least one positive entry. This is one such example. Let A be an almost n matrix whose order is at least 4. So this example cannot be applied. An almost n matrix whose order is at least 4. Then there is a result which talks about the sign pattern of A inverse. A inverse is less than or equal to 0 if and only if A is not a semi-non-negative matrix. Okay, so this n matrix result connects us to the first matrix class that I described, semi-non-negative. An almost n matrix of order 4 of type 1, then it is the semi-non-negative matrix if and only if A inverse has the property that it has not all the entries of A inverse are less than or equal to 0. So A inverse is less than or equal to 0 if and only if A is not a semi-non-negative. Okay, so these are some of the connections that exist between matrix classes that have some positivity property and linear complementarity problem. Now, there are a lot of results that tell you how n matrices of different types have implications for the linear complementarity problem. And the number of solutions for Q, positive, Q, 0, etc. There are lots and lots of results. So n matrices are intricately connected to the linear complementarity problem, but I'm looking at the other end where positivity properties of these matrix classes can be studied. Okay, so I would like to stop here. There are always these working questions that if the matrix is not invertible, one can talk about almost n naught matrices, n naught matrices. Professor Niyogi and collaborators, Deepthi, I think even Pratap. So they have studied these matrix classes. So there is always this singular thing that lurks behind all these results. So one can ask whether analogous results exist for singular. That is when you consider the Wolf inverse inverse or the group inverse. I think there is quite a bit that can be done and looks not real as well as interesting. So this is just to give you a few of such results. I'll ask you to look at my paper that appeared in Annals of OR. It has documented a few more such possibility results and some open questions there also. So I would like to stop here, Manidi. Title is Professor TP's contributions to LCP. Professor T. Parthasarathy. TP's contributions, T. Parthasarathy's contribution to linear complementarity problems. This was like a survey paper which also included some new results. Myself, Sushmita, and GSR Murthy from ISI Hyderabad. This appeared in 2020, Annals of OR. There is a lot of questions that I have posted in that paper. If there are any questions, I can try and answer.
So the notion of almost n matrix, type 1 and type 2. So similar kind of notion है for almost P matrices.
Yeah. All principal minors are positive except the determinant, which so the inverse of an almost N matrix is an almost P matrix.
Is it also a type 1 and 2 like kind of N matrices?
For N matrices, yes, and for almost N matrices, but not for P matrices. I mean, not for almost P matrices.
Sir, I just to ask.
Yeah.
That these submatrices, submatrices.
Yeah, principal submatrices.
M matrix also.
Yeah. All the sub, yeah, something by induction you can show this.
Well, I mean, this kind of, I mean, affix classes has been studied that where property has been preserved by the submatrices.
Yeah. See, for Q, this is not true, for example. So, lot of properties for M matrices are similar to the properties for P or the positive definite matrix, for example. But I mean, such questions can be asked. Such questions can be asked for the other classes also. Principal pivot transform, principal submatrices, whether it's closed with respect to the transpose operation, diagonal similarity, scaling, all kinds of things. A matrix is called completely Q if all the principal submatrices are also Q. And there are some categorizations of completely Q matrices.
So another one is this then this and negative non-positive.
Yeah, this one. A is a Q matrix, then identity minus A has a non-positive, right? Yeah.
Like for example, because the linear LCP, then it the left hand side is matrix becoming like that. I think and then W and Z, and we can convert it to this matrix and to that.
Yeah.
So that's the thing that this the converse with. I mean, probably that's the reason we come in here. That has a non-right inverse. Is the solution something?
You are asking about the proof, right? See, for one thing, not true. I mean, I have given an example there. That paper. The converse is not true. So can we identify matrix classes A for which the converse is true? That is one interesting question that can be attempted. The proof just uses feasibility, not even solvability. For every the next subset use non-negative. All is being used.
Another thing is that, for example, this is I mean co-positive matrices.
Yeah.
For which the feasibility I mean solvability.
Yes.
So for such kind of matrices, this converse or not, because the reason is I can see that if with the complementary pivot algorithm applying it, as it comes to something with the inverse and it becomes positive, right? So the converse is at least it is.
Yeah. Okay. So you are asking this question for special classes of matrices now. I have no idea, but it can be feasible.
This is something we are when we are applying this complementary pivot algorithm.
Yeah.
So it's becoming that few classes and matrices for which this algorithm really works. And it has a solution. Feasibility implies the solvability. So L matrices is one of the classes and matrices. So you can see that for the converse is And I don't know.
Yeah, one can use. Yes, I agree. See, co-positive does you. So what you're saying is that co-positive plus this condition will like you. Yeah, that's Some we can. I have no idea. I don't know whether the answer is yes.
I'm also not sure how to approach this. That's all from my side. Any questions from any of the people? Okay, so I would like to thank this is for spending time, like almost for all the lectures, and he raised few of the problems whether with Michael and so everyone will try. I mean, try solving that problem. And, I personally would like to thank you, sir, for conducting it. I know that at some point I'm not able to conduct the Gen course. Always inspire me. Okay, that yes, I can do. So thank you, and you always suggest me. Started from the beginning. That's the I mean I'm really thankful to that. I without your advice or suggestion, but don't not it's possible for me to conduct it. And yeah, it's you are always so approachable.
Pleasure with you, and hope to collaborate further.
Yeah. I mean, I'll be happy. I mean, and I was expecting also that I'm here, but it was not possible this time. Maybe.
Only when Mike makes it, we can probably come together, something like that.
I would also like to conduct something later on sometime that all of you can come and the participants also come here so that they can physically collaboration. I believe that post is really helpful because lots of information got it. This what is going on, what can be done. So, thank you, sir, and I would like to thank again also for sponsoring course and of course the participants.
Yes.
Thank you here for actively participating in the course. Because in the last course what I conducted online, I didn't have that much good experience. I was a little bit worried also that I can participate. So, and I'm pretty sure everyone has enjoyed it. I really enjoyed it. Even started in the morning, but I really enjoyed it, and I'm happy that I conducted it. And thank you so much, sir, for helping me. Started from the beginning, and
Congratulations, you have made it possible.
Thank you so much.
And thanks to the participants for the.
Thank you so much, sir, for wonderful.
Thank you.
And, sir, you taught a lot, 1 or 2 days. So, we can have a problem later. We will think about it, whatever you did. So, can we contact you later?
Absolutely. Most welcome. Yeah.
Because it is little difficult to think all the things which you have discussed here. So, we think about it, and we can contact.
Sure. Anybody, anytime.
Thank you so much, sir.
Thank you.
Thank you very much, sir.
Yeah, thank you. Sunil is not today. Okay. Manideepa?
thank you, sir. Thank you so much for your time also. And I hope that we will see you soon.
Yeah, sure. Bye-bye, everyone. Thank you.
I have a quick few announcement for the participants. So you know that on the schedule there is an exam over there. So I have already that I'll be free. So please try to appear on the examination, and the feedback form also shared to you. Please fill it up, and also on the GAN portal also once you get a options of feedback up, and I already shared actually. So any concern or anything, you can email, call me. You have my mobile number also. You have my email also, or you can WhatsApp me also. So any concern or anything from the participants?
What type of a question in like objective
It
or
will be only MCQ only, because I'm going to share the Google form, so you just. So maybe I'll sometimes I'll send it sometimes, and I'll give 1 hour. I mean, you don't need to back it; you just need to submit it form. And another important announcement is I'll be sharing another Google form where you can you have to fill up your address so that I can post the certificate.
Okay, ma'am.
So anything else?
When will be the quiz?
Sometimes today after.
Okay.
Then you can come to have it at night, and then you can I'll just night or something.
Through mail, right?
Yes, through mail only. I'll send it the link. So I know that because many working or having some classes will be busy at time at night time also after the work hour.
Okay, will there be any time bound for that actually? Like,
No, I don't think I'll give it that much of time bound.
okay,
Maybe night today or maybe tomorrow.
okay.
The thing is that you just need to submit the examination. So I need it for generating the certificate.
Yeah, got it.
So certificate definitely I'll email to you, everyone. But I need your address, proper address with the PIN number and everything. So it may take a little bit of time. So I hope that I can able to do the coming week.
Okay.
And
Okay,
thank you,
thank
so
you.
much,
Thank you very much.
for conducting such a wonderful workshop on LCP. We are really thankful.
Yeah, thank you.
Yeah, thank you. And I thank to all of you for really, active participation, because as I already told in my last also, I conducted some course in online. I didn't have that great experience. But here you are really active, and I believe that it's really helpful for all of you. And you listen it so carefully, and you participate also so actively. So thank you very much. And I hope that sometimes we can see it physically. Maybe let me conduct something. I'd love to see you all on that particular course, or maybe some workshop or conference.
In future, if you will conduct a course or conference, definitely we will be there.
Okay then, it's bye from now, and thank you once again to everyone.
Thank you, ma'am. Bye.
Yeah, thank you, ma'am.
Thank you so much, ma'am.